Good morning, everyone. Welcome to Chemistry 1406. My name is Dr. Fongno, and I will be your instructor for this semester. I know it is a little weird having to learn chemistry over a webcam and video, but in these uncertain times, we're going to do the best we can with what we have. Just in case you're wondering, because I wonder about these things sometimes too, this background I have behind me is actually real. It is a real bookcase, and you can take things off of it. For example, this lightsaber that I built out of 3D printed parts. It's a raised lightsaber. Um, I'm building a second lightsaber, except that it's fully functional, so it's taking me a little bit longer to build that one. Anyway, let's go ahead and get started with the class. I'm going to maximize the PowerPoint window now so you can see the presentation. There we go. Today we'll be talking Lecture 1, but before we even get started, you might be asking yourself, why is this guy even qualified to teach the class? What would I do during the day? Who am I? I'm actually a forensic scientist that works here in the DFW area. To get there, I actually have a few degrees. I have a degree in biology, a degree in chemistry. I have a master's degree in chemistry, and I also have a PhD in biochemistry. So all that gets me uh, into these organizations like the American Chemical Society, the American Board of Criminalistics, the Association of Firemen and Tool Mark Examiners, that's a forensic science group, and then also the American Academy of Forensic Sciences. Yeah, when I was a kid going through school, I was pretty indecisive. I did not know what I wanted to do with my life. That's why I decided to stay there as long as I could, get as many degrees as possible, I guess. What do I do, though, as a forensic scientist? I mostly work homicide cases. I investigate them. Homicide cases, assault cases, robbery cases, burglaries, and weapons cases that involve firearms. You might be wondering about the meme there to the left that has me in there in front of actually the Colt factory. It says, "Honest, Your Honor, I am a forensic scientist." It actually calls back to a time when I was working in Alabama and I was in a courtroom and the judge didn't believe me when I told him what I did for a living and what my job was and that stuff. It's a funny story. I might tell you guys about it someday. But let's go ahead and get into more important things. Probably the most important thing today we'll be discussing is going to be the uh, syllabus. So let me minimize the PowerPoint presentation and maximize the syllabus real quick so we can talk about that briefly. Hang in there. Hang real quick. There we go. There's the syllabus. All right. So the most important thing about the syllabus is uh, probably going to be my contact information, which is right here. Um, my contact information includes my office address, my phone number, and my email address. But you're probably best trying to reach me by email. I'm pretty quick about the emails, and if you need any help, just please try to contact me by email first. The required textbook for the class is going to be Chemistry: An Introduction to General Organic and Biological Chemistry, the 13th edition by Karen C. Timberlake. It's not absolutely required because most of the things that you'll be learning in the class and that will be on the exams, assignments, and such are going to be in the lecture videos. But we do use the textbook as a guide, so it's good to have, but it's not absolutely required. What is required in the class, though, is in this next section. I highly recommend a Texas Instruments TI-30 series calculator. It's my favorite calculator to use. I used it when I was in chemistry class, but really any non-graphing calculator is appropriate. But I really recommend the TI-30 series. I'll show you why later on in the lecture. You also need a computer with internet access and a webcam. You need to have Microsoft Office, and you need to have Adobe Acrobat Reader. All this stuff will be required for the class. So one other thing that's also required for the class is Proctoro. So your exams actually will be taken at home on your personal computers, but there will be remote proctoring being done by a third-party company called Proctorio. Uh, and it's actually required now for all of the TCC online classes. We'll actually get into more detail about that later on in the syllabus. So let's talk about the grading criteria. The lab is actually worth 25% of the grade, and the lecture, which is this part, is worth 75% of the grade. The 75% of the grade is broken down into three parts. 10% of it is actually the daily assignments, the quizzes, and the online participation. Your exams, there are four of them, and they're worth 40%. And then the final exam itself is actually worth 25%. You'll be interested to know that the lowest grade of all your daily assignments will be dropped, and also the lowest grade of your lecture exams, of the four lecture exams, will be dropped as well. And again, the laboratory is actually worth 25%. It won't be starting until later on today, on Tuesday. So we'll go over that breakdown in the actual lab syllabus. The grading scale is pretty normal. You can read that for yourselves. It's not different from most people's grading scales. But I think the one thing that is very interesting, or thing that to take note of, is that this class is normally taught as a face-to-face class, but because of the times that we're in right now, we have to make this an online class. So all of your course materials, exams, lectures, notes, and assignments, they'll all be distributed through Blackboard. And so it's important to be on your Blackboard every day. So, primarily you'll be getting most of your information through lecture videos like this one. They'll be based on the schedule of topics that are in our class schedule. And usually they'll be covered pretty thoroughly in a 60 to 90-minute video lecture like this one. They'll be posted about 2 times a week, generally on Tuesdays and Thursdays at 8 a.m. I'm treating this like a Tuesday-Thursday class, even though it's online. That being said, you can watch the video anytime you want, but there will be assignments attached to it and quizzes attached to it, so we'll talk about that in a second. Like I was already saying before, we use the textbook as a guide, but most of the material you'll be responsible for you'll be getting through these lecture videos. So with every lecture video actually comes a quiz. This quiz is actually based on the lecture video from the day before, from the class lesson before that, right? So today there is no quiz because this will be the very first official lecture. And they'll be, like I said, generally based on the lecture before. They're usually going to be about 10 to 20 questions long, multiple choice, and you can actually use your notes and your textbook on these quizzes. But you only have 30 minutes, 15 to 30 minutes to take the quiz, depending on how long it is. And the quiz will be available for 24 hours from the time it's posted for you to be able to take the quiz. It will be due at the end of the 24 hours. You only have one chance to take it. You only have one sitting to take it in. So best to use the notes that you take during the lecture videos to do your quiz. Yes. So let's see here. Next will be our daily assignments. Daily assignments also come along with the lecture videos too. Those are going to be based on the actual lecture video that's posted. So today's lecture video, which is lecture 1, will have the Blackboard assignment 1 attached to it, and so on for the rest of the semester. These can come in the form of all kinds of different things. At the beginning, I'll probably stick to multiple choice worksheets because these are the less interesting things about chemistry. But they can be anything from worksheets, watching supplemental videos and posting about them in a forum, working practice problems, answering discussion questions, and just participation in online events. So that's what your daily assignments are. Usually they'll be available for 48 hours. That means they'll be posted with the lecture, and by the time the next lecture is available, you would have had to already finished the assignment for the previous lecture, the one that's currently due. So they're designed so that you work on them immediately or during the actual video lecture itself. I may change it a little bit though, since it's a Tuesday, Thursday kind of sort of thing I want to go here. And maybe the ones that are on Thursday will be due right before class on Tuesday mornings, but I haven't quite decided that yet. And then last but not least, in this online class online class structure, is we have the exams. Like I already stated before, your exams will be taken online at home on your own personal computers, and they'll be supervised or proctored by a third-party service called Proctorio. There is a link down here that will take you to Proctorio, and it will actually show you how to install Google Chrome and Proctorio, because you have to have Google Chrome for this to work. So open up your Blackboard and then go into the exam using Google Chrome, and then the Proctorio remote monitoring service will work. Exams will be posted by 8 a.m. on the day of a posted exam, and they will be due that same day by 11:59 p.m. So once you've entered the exam, though, you'll have 60 minutes to complete it. You cannot exit the exam for any reason, because you have to complete it in one sitting. Um, so if you leave the exam for any reason at all, it'll kick you out, and then your exam will be graded as is. So just to review about exams, they'll be monitored by Proctorio. You have to finish the exam within one sitting. You need to have a webcam, microphone connected to your computer for the exams. And you'll need to have also ID for verification to make sure you are actually the one taking the exam, the one taking the classes, taking the exam. During the exam, though, you're absolutely not allowed to open any other browser windows, access your textbook or notes or anything like that. They're not like quizzes. And then you're not allowed to take any photographs, screenshots, or print any portion of the exam or visit any other websites while you're taking the exam. If you fail to comply with any of these instructions, you will be assigned a 0 as a grade for that exam. The thing you are allowed to use during the exam, though, is a TI-30 series calculator, or any non-graphing calculator. Again, I highly recommend the TI-30. It's the easiest one to use. I'll show you about it later. The other thing you have, too, is that you might need to do some scratch work, and scratch work cannot be done on paper and pencil. It must be done on a digital whiteboard that will be available to you inside the exam itself on the screen. I do have office hours. Even though this is an online class, there are Tuesdays and Thursdays from 4 p.m. to 5 p.m. If you need any other time than that, just email me and we can set something up. We'll have our office meetings actually in Microsoft Teams. There's already been a team set up in Microsoft Teams for our class, so we'll use that. We'll use that to do discussions as well, but mostly we'll use it for um, office hours. And if we go down one more page, then this syllabus is actually posted on Blackboard, so you can download it and print it from there if you'd like. This is our class schedule. Notice we have a free day. Friday didn't work out very well as the first day of the class, so I'm glad I moved it to Tuesday. So now lecture 1 will be on Tuesday right here. There will be no quiz on lecture 1, but there is a homework assignment, which is actually already posted, but it'll be available all the way until the next lecture for you to finish. You can read the schedule for the rest of all the lectures and our topics we'll be discussing, but the most important thing to notice here is that you do have exams on February 11th, March 4th, and April 1st, and on April 29th. And then your final exam will actually be on May 7th, right here. We'll have a little final review session just to help you out. I know that stuff from the very beginning of the semester might be difficult to remember, so we'll have a little final exam review. Probably do it in teams, but we'll see how it goes. And that is the syllabus. If you have any questions about the syllabus, please let me know through email or something. Okay, so let me go ahead and maximize the PowerPoint again, and we'll get started with actually some chemistry now. There we go. And then start the PowerPoint. Looks good. All right, so the first thing we want to ask ourselves in this chemistry class is a very obvious question, and that question is, what is chemistry? Well, chemistry actually is the scientific study of the composition, structure, properties, and reactions of matter. So, will you take this protein right here on the left? Oh, sorry, on the right, as our example. This protein actually is called hemoglobin, and my structure came up a little bit too fast, but that's okay. We can still keep going with this. This is actually a protein called hemoglobin. And let me actually make my pen work so I can actually draw some stuff for you. Technology these days, so amazing. In fact, I'm going to go ahead and back up one thing so that you don't see that structure because I need some room. Okay, so this is actually hemoglobin. Most of you probably know that hemoglobin is in your blood, right? And what does it do in your blood? Well, there's a very special function. It transports oxygen through all the cells, sorry, not through, but to all the cells in your body. That's what it does. So let's use this protein, hemoglobin, as our example for what is chemistry in its definition. What is the composition of hemoglobin or your blood? Right? The first thing is composition. Well, proteins are actually made of these things right here that are like swirly things. They're called alpha helices. These are all random coils, and they're all made of very specific things called amino acids. We'll talk a lot about amino acids later on in life. I mean later on in the semester, not in life. But they're all amino acids. But mostly, the most important thing that hemoglobin is actually made of is actually in the center. And in the center is a molecule called heme B. Alright? So let's take a look and see what heme B actually looks like. Hopefully my writing didn't cover anything up. Oh, it did. That's okay. That's not the important part. So this is the structure of heme B. We answered that question now. Structure. It's actually a very important structure because it's what we in chemistry call a tetrapyral molecule, because there are these guys right there with the double bonds, the 5-membered rings with the nitrogen side. Those are all called tetrapyrals. Sorry, actually they're called pyrols, and there are 4 of them, right? And that's why it's called a tetrapyral molecule. Interestingly, when I was in grad school, I did a lot of work with tetrapyral molecules. The one I studied was actually called luciferin, and it actually made, when it bound with an enzyme, a special enzyme called luciferase, it actually glowed blue. So that was a pretty cool protein right there. The most important part of this heme, though, is this guy right here. It's an iron that's in the center of the heme, right? And that iron likes to interact with oxygen. So that's the properties. Interaction with oxygen, right? That's what the heme does there, right? You take a close look at that heme, and you see a 2 next to it. What does that mean? That 2 actually means that the iron has a +2 charge, right? But it likes oxygen, and oxygen likes it, right? So when you bring oxygen into the mix, the iron actually becomes a +3 charge, right? Why does that happen? Well, it's because oxygen is, I don't know if you remember this or you have heard this before, but oxygen is actually very electronegative. What does it mean to be electronegative? Let me spell that right. Electronegative. It means it loves electrons, right? It'll take them from other atoms. And here it took an electron from iron. So when you take 1 electron from iron, it goes from a +2 charge to a +3 charge because it's 1 electron less now, and electrons are negatively charged, which is very interesting, right? It's also very interesting because this is actually the difference between deoxygenated blood and oxygenated blood, right? Oxygenated blood has an iron, an Fe3 +3 charge, right? An iron with a +3 charge, whereas deoxygenated blood has an iron with a +2 charge. And you can actually see this with your eyes, because a deoxygenated blood actually has a dark red color to it, whereas oxygenated blood has a very bright red color to it. Bright red. color to it, right? Very bright red. These actually correspond to wavelengths of light um, in the uh, in the visual spectrum, and the dark red is actually 940 nanometers, and the bright red is actually 660 nanometers. Interestingly, I was talking to you about luciferase and luciferin earlier. Luciferin, when it turns blue, that bright blue color I was talking about, it's actually 475 nanometers. Is blue. Very bright blue, right? So back when I was in college, I had a professor named Dr. Chastain, and he would always ask us what our favorite color was. Well, he didn't want you to actually tell you what the color was. He wanted to know what the wavelength was. So he would always say that his favorite color was 663. He didn't say 666 because that'd be kind of weird. So it was 663, right? What is 663? Well, actually, 663 is super close to 660 here, right? So 663 is then what? It's red, very bright red, right? So people ask me what my favorite color is now. I always say, oh, it's 475, which is blue. If you take a look at the visible spectrum, you can figure out what your favorite color is too. Why is that even important? Well, have you ever gone to the doctor or gone to the emergency room and had to use a pulse oximeter? I don't even know how to spell pulse oximeter. Is that how you spell it? There we go. It was the meter part that I didn't know how to spell. Anyway, a pulse oximeter actually works on this change in wavelength right here, right? This change and the difference between those two numbers is how a pulse oximeter, one of those things that goes on your finger that determines how much oxygen your blood has, right? The difference between that number, 940 and 660, is how a pulse oximeter works and tells you what your oxygen content is. So next time you go to the doctor, take a gander at it. That's why there's you see a little light in there, and it's a little red light that actually can go penetrate your skin and see what color your blood is, and that's how it tells how oxygenated your blood is. Kind of interesting. So, how do we, as scientists, study chemistry? Well, like I already said or alluded to, you have to think like a scientist, because And what does it mean to think like a scientist? Well, it means to solve problems using the scientific method. And most of you already know this. Most of this lecture will be a review. But you begin with making observations, right? And from these observations, you can propose problems that need to be solved, or questions that need to be asked, whatever they may be, right? But once you have that problem or that question that needs to be solved, right, you come up with a hypothesis. And a hypothesis is basically a super educated guess. How do you spell educated? I'll get there. Educated. There it is. Educated guess. There we go. A super educated guess on what you think might happen. And a lot of people don't like the word guess, but it really is a guess. You're thinking about what's going to happen based on your previous experience and knowledge about the topic, right? Once you figure out that, some kind of guess or hypothesis on what the outcome will be, you design an experiment that will give you data. And that next step then is to analyze that data. And after you analyze that data, you can, in your conclusions, confirm or decline your hypothesis. Yes. And if you have confirmed your hypothesis, meaning your hypothesis is right, good for you. But if your hypothesis is incorrect and has to be declined, then what do? Well, you have to go back to the experimental stage, come up with a different experiment, and do it again. And let me tell you, it happens all the time. So don't feel bad if you have to decline your hypothesis the first time. So I'm going to use an example from my life to demonstrate this, right? So when I work at the crime lab, a very common question that's asked is there a struggle, right? What I mean is there a struggle? Well, generally when two people get into a fight and one of them has a gun and they're struggling, the gun can go off like accidentally. Well, the person who shot the other person can use that as an excuse that, oh, it's an accidental discharge. I didn't mean to shoot him, right? Well, that's why it's a question that needs to be asked forensically, right? They can't use that as an excuse anymore if they were actually far away when the gun went off and the guy got shot. So, as a forensic scientist, what do I do to figure out whether or not a person was in a struggle when they were shot? Taking a look at, when you fire a gun, though, you see that a plume of smoke comes out with the bullet. This plume of smoke is actually filled with things called GSR, or gunshot residue. We'll talk about more specifically what that is in a second. But then also, once a target is hit, and this is actually a black t-shirt that was shot, no one ever gets shot with a white t-shirt on. It would make things a lot easier. But if you look really closely, you'll see these little speckles of black right here, shiny black. That's gunpowder. That also came out when the gun was shot, right? So you'll get this mixture of like burned gunpowder that caused the explosion that made the bullet fly out the barrel of the gun, but then you also get some unburned gunpowder too that will fly out of the barrel with the bullet and hit the target, right? And that actually sticks to the target, and that helps us with our forensic analysis, right? Why does it help us with our forensics analysis? Well, it's because if there was a struggle during the discharge of the firearm, then all this GSR or gunshot residue should be all over the person that was shot, right? But if the guy was far away when he shot the person that he was fighting with, right, there wouldn't be any of these things present, right? So how do we tell? Guess what? We use chemistry. I have a hypothesis. This is my problem right here, right? This is my problem. Was it a struggle or not? Well, my hypothesis is that, there's a stuff present. Maybe he was close. Maybe there was a struggle, right? So what is the experiment going to be? Well, turns out there are several different chemicals that you can use to detect gunshot residue. One of them is actually called sodium rhodesonate. And what it does is that when it binds to lead, and lead is a part of gunshot residue, you don't really need to know the actual reactions that are occurring here. You just need to know that rhodesonate turns purple in the contact when it comes in contact with lead. It's detecting lead, which is also known as PB, lead. It turns purple, right? So what part of gunshot residue is actually lead? Well, the primer mixture has lead in it, right? In a actual cartridge, where the bullet actually originated from, there's gunpowder inside the cartridge case, and then outside the cartridge case, there's a little primer that when you hit it makes a little tiny explosion. When you hit it, that's from the firing pin hits it, and there's this little tiny explosion, and that little tiny explosion is what ignites the actual gunpowder, and that gunpowder is what then expels the bullet from the barrel. So that little primer right there with a small explosion actually has a compound in it called lead stephanate, and lead stephanate is present in mass quantities in gunshot residue, and that's actually what you're detecting with sodium rhodesonate, the lead stephanate. Bullets are also made of lead too, but really we're looking for the lead stephanate from the primer mixtures. There's another test that you can do too, right here, called the modified Grice test, and it's got multiple different chemicals in it that will react and give you an orange color in the presence of NO2 minus. So NO2 minus is actually nitrite, right? And nitrite is the component that is left over after gunpowder has burned, right? Gunpowder is burned, and then now you have the nitrite ion, right? And in this case, during the modified Grice, you're detecting nitrate, and if you have a lot of nitrite around, that's also indicative of someone being very close to the person when the gun discharged. Last but not least, in the gunshot residue detection, right, is we have a molecule called diphenylamine. And diphenylamine, when it actually comes in contact with gunpowder itself that hasn't been burned yet or exploded yet, it's actually NO3 plus, or sorry, NO3 minus. This is the nitrite ion, right? Just to be clear, NO2 is nitrite, NO3 minus is nitrate. That's unburned gunpowder. So diphenylamine, when it comes in contact with nitrate ions from unburned gunpowder, it actually turns blue. So there's another way to detect whether or not there was gunshot residue that's present on the victim when they were shot. And then over here we actually have another molecule called dithioxamide, right? What it does is that it will combine with copper and turn green. Why do we need to detect copper? It turns out that a lot of the bullets that we find in casework, they are bullets. Most commonly they're bullets that are copper jacketed, right? The bullet itself is lead inside, and then it's jacketed with copper on the outside, right? And so when you're looking at like a bullet hole in a shirt, you need to make sure it actually is a bullet hole and not from somebody just tearing it with a knife or something like that, or just tearing a hole in it, right? Well, how do you do that? Well, the copper, as it passes through the shirt, will leave behind some the copper from the bullet jacket will leave behind some copper in the bullet hole when it passes through the shirt, and then we can use this molecule right here, the dithioxamide, to confirm that that bullet hole was actually a bullet hole and not something else, not caused by something else. So all these things together, if you see, are present on a person when they're shot, generally means that the gun was close to them when they were shot. So we can use that as a tool, along with many other things, other evidence, as a tool to ask and answer the question, was it a struggle? Interesting stuff. So, moving on, how do I actually get good at chemistry? Me personally, how did I get good at chemistry? Well, it takes a lot of study and a lot of practice, but most of all, it takes a lot of math. I would say that the most difficult part of chemistry for students, in my experience for students, is connecting the math concepts to the chemistry concepts, right? They consider chemistry the central science. For one thing, it's because it connects the physics with the biology. It's right in the middle, right? You can't have either one without chemistry in the middle. But another reason why it's the central science is because chemistry is also considered a physical science under the formal science known as mathematics, right? And so math is like required to do chemistry. So it's very important that we have a good foundation for mathematics. In mathematics when we do chemistry. Yeah, if you didn't already know that, science is actually built on this hierarchy where the formal science, or the top level, is mathematics. And below that is the physical sciences, like physics and chemistry. And then below that is the life sciences, like biology. And then below that is the applied sciences, like forensic sciences, food sciences, things like that. So chemistry is right up there in the middle of everybody. So how do we get good at chemistry? We've got to do some math. So I want to go through some review here of some very simple math skills just to make sure that everybody's on the same page for the rest of the class, the rest of the semester, because you will need these skills. So let's review. Let's do a little math review real quick. The first thing to talk about is decimal places. If I could spell decimal places. There we go. Decimal places, right? If I have a number like 2518.407 grams, if I have a number like that, right? What are each one of these places called? I know this is simple stuff, but we still have to make sure that everybody is on the same page. Starting over here, that's called the thousandths place. The second place behind the decimal is the hundredths place. And then the place right after the decimal is the tenths place. right? The spot right in front of the decimal is the ones place. Right before that is the tens place. Right before that is the hundreds place. And right before that is the thousands place. The thing to remember is that the places after the decimal point are the same as the places before the decimal point, except for the ones place, and after the decimal point, they always end in tenths, right? They always end in tenths. So that takes us to talking about then how we usually deal with numbers in chemistry, and that is with scientific notation. Scientific notation, right? So I have a number like 2400. What is that in scientific notation? Well, the decimal point is right there. If I move the decimal point over 3 spots, I get to where the 2 is in the ones position now. That means then that in scientific notation, this is 2.4 times 10 to the third power. Why is it the third power? It's because I moved over 3 spots to get 2 to the ones place. Right? Let's do it backwards now. If I have a number like 0.00086, how many spots do I have to move over to get 8 into the one spot? So we'll say that this is then 8.6 times 10 to the what? It's actually negative 4 because you're going backwards. Right? Negative 4. What is all this based on, actually? Well, it's based on this. It's called the power of tens. The power of tens, right? So we have 2400 right here, or 2400. Just to make it easy on ourselves, we'll say that that is like 1,000, right? Well, how do we get to 1,000? It's actually 10 times 10 times 10. And then that makes it so that we can write it in scientific notation as 1 times 10 to the third. Right? And then for behind the decimal point, we'll say we'll have a number like 0.001 or 1,000ths, right? Well, that really is just 1/10 times 1/10 times 1/10. So that gives me 1 times 10 to the negative 3. That makes sense, right? So this will be the basis for our calculator demo. I'm so sorry, I didn't even realize you couldn't see there. My face is blocking that. I'll write the answer up here. There we go. Nice. So let me do a calculator demo now to show you how we use scientific notation in the calculator. So that is a pretty old calculator. I used this when I was in college. It's my TI-30X2S, and it's my favorite calculator to use. And we'll take a look at how to do scientific notation here. So hopefully I don't screw this up. So the button that you need to remember when you're doing scientific notation on the calculator is this one right there. That's the double E button right there. See the double E? The way you access that is by hitting second, right? And then double E. And then you get that E there. E stands for exponent, right? So for example, I can clear this out and we'll use one of the numbers that we just used on our screen over here in our example. I have 2400, right? Actually, what I'll do is show you that 2400 is equivalent to, how we would type it in as scientific notation would be 2, so you can see the numbers, 0.4, right, times 10, which you don't even have to put in the times 10 part because you're going to use the E, right, and that was 2 to the third. And you press enter, you see that you get 2400. And that's how you do scientific notation. It works the same way behind the decimal point as well. So we had the number 0.00086, right? That's what we had as one of our numbers in our current example, okay? Let me clear that out and we can actually type in what we got as our answer. Writing it by hand in scientific notation, 8.6, right? And then second, E. Remember, you don't have to type in. You could if you wanted to, but you don't have to type in the times 10 part because that's what the E stands for. And to the negative, by the way, this down here, sorry you can't see it, this button right here is the negative sign, right? You don't use the minus sign, but you use the negative sign right here. It looks like a negative inside parentheses. You put negative 4, and when I hit enter here, we should come up with 0.000, yeah, 0.00086. Well, it just rounded off to 0.001. But how do we change that so we can actually see everything? Right here, you can hit the second button again, and then hit the scientific or engineering button, right? And there's flow, science, and engineering. If you change it to science, you'll see what happens. See? 8.6 times 10, or yes, times 10 to the negative 4. I am not quite sure why I rounded it before though. I generally keep it on flow though, because I like to see all the decimal points. I'm not sure why it rounded there. Let's see here. Engineering is weird. We're definitely not engineers. We'll go back to scientific. Okay. So no matter what, if you're under scientific, it will be able to give you the number in scientific notation. But generally we keep everything in the flow. Let me try that again. 8.6 E to the, let's try negative 3 this time. It's rounding up again. I don't know why. Let's see here. 4. There we go. That's what it was. Something was really going wrong there. Somebody set up the calculator. It was my calculator, so maybe it was me. But that's what it's supposed to happen right there. 8.6 e to the negative 4. And that gives us 0.000086, like we do have over there on our example. Sorry about that. That was really weird, but we figured it out. So that's a tip for you, because something might happen with your calculator while you're doing a test or an assignment or something, and it's coming up with some weird numbers like it just did for me. The first thing you need to do is clear the memory. And you do that by hitting the second button right there, and then hitting the 0 right there, because 0 is reset right there. Right? The 0 button is reset, but only under second, right? You have to go to second first, then hit the 0 button for reset. All right. So after talking scientific notation, let's talk about, we were just already saying negative and positive numbers, and the negative scientific notation numbers were giving me some problems on the calculator, but we cleared that up, right? So let's talk about positive and negative numbers. And the way that people most describe positive and negative numbers is with a number line. So if I start out in the middle, and that is 0, and I go this way, that's 1, 2, 3, 4. But then I go to the left, that's negative 1, negative 2, negative 3, negative 4. 12, that's not what I meant. Ran out of space. Negative 2, negative 3, and negative 4, right? That's important because when we're doing these kinds of things, we need to be able to do the arithmetic correctly with both positive and negative numbers. So I like to actually call it combining numbers instead of saying adding numbers or subtracting numbers or multiplying or dividing numbers. I like to say they're combining. Sorry, just for adding and subtraction, not for multiplication and division. That's a different thing. But I like to say combining when we're talking about the adding and subtracting of numbers. So, for example, if I have something like negative 6 plus 3, what does that equal? Oh, that equals negative 3. Because I was already all the way over at negative 6, and then I'm adding 3 to that, and that gives me negative 3, right? Or if I have something like negative 6 plus negative 3, that gives me negative 9. Because essentially, you're taking away the plus sign, leaving you with just this negative 3 right here, and you do negative 6 minus 3, and you get negative 9. Or you could do something like 6 plus negative 3, and what do you get? That is 3. Because now you're on the positive side, and you essentially just remove the plus sign, and you're subtracting 3, and you get positive 3, right? So, pretty simple, but let's just make sure we all know how to do that, right? I'm going to clear the screen real quick. Good thing it's a video, because if you need to see more, you can just pause it. And you can even see this over here, because I, of course, forgot again that my face is blocking what's there, but it's simple enough. So let's just do something really basic first. And let's say I have an equation like 2x plus 8 equals 14. That kind of looks like a 6. My friends at work always tell me my 4s look like 6s. Let me actually write a 4. There we go. Well, how do I solve for this equation? Well, the goal in solving any equation is actually to get x by itself, right? Because you're solving for x. How do we get x by itself? Well, the first things first. You've got to get rid of this 8 that's on this side of the equal sign, right? And forget that, what I wrote there. But what we're going to do is we're going to subtract 8 from both sides. So remember, on an equation, when you subtract 8 from one side, you've got to subtract it from the other side too, on both sides of the equal sign. And then, so what that gives me then is 2x equals 6. X is almost by itself. What do I do now to get x by itself? Well, I'll divide both sides by 2. Right? And then that gives me x equals what? 3. So that's really the way you solve an equation. Very simple way of solving equations. Uh, so let's use a chemistry example now, right? Let's use a chemistry example, right? There's this thing called the ideal gas law. And in the ideal gas law, there's an equation. And that equation is this. PV equals nRT. And a lot of these things that we'll go over later on in the semester, but just in case you didn't know, P stands for pressure. V stands for volume. T stands for temperature. Right? N here actually stands for the number of moles. And again, we'll talk about that later. A number of moles of a substance. And then, R. Sorry, I lost my train of thought. R is the ideal gas constant. I'm going to keep on writing down here because I ran out of space in the calculator. Actually, I'll just close the calculator down for now. I don't think we need it right now. There we go. The ideal gas constant. We'll talk about that a lot later too. Right? So each of these have different units, right? For example, volume here, the units is usually in liters. The pressure here is usually in atmospheres, right? The temperature is usually in Celsius or Kelvin. In chemistry, we mostly use Kelvin. We'll talk about that later too. And then the number of moles is actually just a number. There's not a unit with that. You'll learn a lot about that later. Actually, you know what? In my notes, I say I should tell you what it is now. 1 mole is actually based on Avogadro's number, right? So 1 mole is equal to 6.02 times 10 to the 23. Wow, that's 6 with 23 zeros behind it. Was that a million? No, a million's only 6 zeros. Trillion? No. Billion is 9 zeros. Trillion is 12. What comes after that? I don't even know. Oh well. Whatever it is, I'll never attain that much in cash, so whatever. Who cares, right? Well, anyway, sorry. Off topic. And so what that is then is that is the number of atoms or molecules in a particular reaction or flask or whatever. Molecules. Molecule. Is there 2 L's in molecules? There it goes. 2 L's in molecules, right? Yes. So this number here is known as Avogadro's number. You'll be seeing a lot of Avogadro's number. Well, I even spelled it wrong in my notes. Avogadro's number, right? Avogadro's number. That doesn't mean that that's what N actually is, but 1 mole translates to Avogadro's number of something, or 6.02 times 10 to the 23 of some substance or atoms or molecules, right? And then the ideal gas constant, which is R, right? Its unit, or that's actually a constant, so we know what this number is, and this number is 0.0821, and it's got a lot of units because it deals with all kinds of gaseous things. It is 18 liters over moles Kelvin, right? That's the ideal gas law with the ideal gas constant. So we'll be talking about that a lot in the gases section of the lecture. I mean, not the lecture, but the semester. But what does that have to do with solving equations? Well, oftentimes you'll be asked to solve one of these for one of these variables given the other variables, right? So let's say you wanted to solve for P from PV equals nRT, right? PV equals nRT, which is the ideal gas law. And we want to solve for P. How do we get P by itself? Well, that's easy, right? You divide both sides by P. Sorry. Divide both sides by V, right? And then you get P equals nRT over V. And then you can plug in all these numbers here, all these variables, the temperature, the ideal gas constant that you already know, the number of moles of something, and the volume, and then you'll be able to solve for what P is. You can do that with any of the variables, right? Say you were looking for in PV equals nRT, you're looking for something like what is the number of moles present in the particular gaseous problem that we have, right? What do you do then to get n by itself, right? How do we solve for n? Well, again, you just divide both sides by RT. And then now you get PV over RT equals n. You've just solved for n, or the number of moles of something in this particular problem. Again, you can do that with any of the variables, right? Very simply, just to solve for those questioned variables. Now that we've talked about equations briefly, let's move on to talking about graphing. So what exactly is a graph? Well, what it does is that it shows you the relationship between the independent variable, right, which is normally placed on the x-axis, right, with the dependent variable, which is placed on the y-axis, right? So science is all about variables, right? Things changing, right? We do something to something, and we see how it changes, right? And so in this case, we have a balloon, and we're raising the temperature of the balloon, so that's the x-axis, right? And as the temperature of the balloon increases, right, so does the volume of the balloon. So we're heating up this balloon, right, from 0 degrees all the way up to 100 degrees. And as we're doing that, the volume of the balloon also increases, right? Also increases, right? We start out here at 0, and we're going up to 100, and you can see in the picture and in this line that it's going up and to the right, which means that it has a direct relationship. Turns out that volume has a direct relationship, there it is, with temperature when we're talking about balloons. If I can write out the word balloons. There we go, when we talk about balloons, right? So that's really interesting because there's a lot of things you can determine just by looking at this graph, right? So one of the most important things is the fact that I'm actually going to clear this out so I have some room here. So we've already established that it's got a direct relationship, temperature and volume when you talk about heating up a balloon. Remember that the x-axis or the dependent variable always depends on the, did I say x-axis? I'm sorry, that's the y. The y-axis or the dependent variable always depends on the x-axis or the independent variable. That's very important, okay? But this line here that shows us that we have a direct relationship here with temperature and volume in regards to this balloon, this line here actually has a very special equation. And this equation is called, whoops, I messed up there. That's not the equation. It's y equals mx plus b. It turns out that any line on a graph has an equation, but when it's a straight line like that, it's y equals mx plus b. Right? So what are the parts of this particular equation? We'll start out with this, the y. The y is the y variable, so whatever number on the y-axis or value on the y-axis that you're interested in. And then x is whatever value or number is on the x-axis, right? So that's an x value, and this is a y value. That doesn't even look like the word value. Value, there it goes, right? And remember, y depends on x. Over here, b is actually known as the y-intercept, right? On this particular graph, the y-intercept is right here. It's just above 22. We don't know the exact number, but it's just above 22. It's not right there at the point of the graph, right? So it's just above, so we're not really sure what the y-intercept is. But let me tell you, we can figure out what the y-intercept is just from the data on this graph, right? And probably the most important part of the y equals mx plus b equation is this. This is the slope of the line. The slope tells you the relationship, and you get most of your information from this equation and the slope, right? So let's do some math and figure out, some things about this graph here, okay? What is the slope? Well, the slope is known as rise over run, or the amount the value increases in the y over the amount of the value increasing over x, right? So these coordinates, by the way, right, all these different points, they have a very specific annotation, not annotation, but syntax, or way you write them. It's always x comma y, right? And if you want to figure out what the slope of this line is, right, all you have to really do is go to points on the line that you do know what the x and y are, and put them into the equation to figure out what the slope is. So slope, or m, equals the change in y over the change in x. So a second ago I said rise over run, right? Rise because this is the change in y and it's going up, rise. And then run because this is the change in x and it's going that way, and it's running to the right. It's not rising, right? And the equation to figure out what the slope is m equals x, oops, I messed up, y2 minus y1 divided by x2 minus x1, right? So that's what that means when I say the change in y, which is the second y value minus the first y value, divided by the change in x, which is the second x value minus the first x value. So let's clear this off and see if we can see any numbers we can use on the graph, right? Any points that are easy. Well, here we go. We have this one right here. We can see that the x value for that point is 20, and then the y value for that point is 24, right? So this would be x1. Oops, I drew a y for some reason. This would be x1, and then let me make it a little bit clearer. That's just such a bad handwriting. There we go. That point right there, and this 20 here would be x1, right? And then this 24 over here, right, would be y1. So how do we choose y2? Well, let's see if we can find a point that we can use. Oh, this was good right here. I think this is really good. That point's good, right? Because it's exactly in the middle right here between 80 and 60. So that's got to be 70, right? So 70 here will be x2, right? And then that one's on that line right there. And so we go to the line. It's 28. That would be y2. I don't know why I did that. Why did I underline the x values and circle the y values? Who knows? So let's plug that into our equation, right? So if you recall, m, or the slope, equals y2 minus y1 divided by x2 minus x1, right? So what does that equal then? Let's plug in our numbers. y2 is 28, and then y1 is 24. divided by x2, which is 70, and then minus 20, which is x1, right? And then that will give us our slope. So this is just easy arithmetic here, right? 28 minus 24 gives us 4, and then 70 minus 20 gives us 50. So that is 4 50ths. Let's reduce that a little bit. If we reduce that down, that actually becomes 2 25ths. So that's the rise over run, or the slope, right? So as we look at our y equals mx plus b equation, right, we've figured out what the m is now. The m is, for every 25 spots on the x-axis we move to the right, we move up 2 spots on the y-axis. That's our slope, right? Cool. Well, now that we have our slope, we can figure out all kinds of stuff, right? For example, what actually is the y-intercept? B. What is that? Well, this is actually really simple to do now that we have the slope. We have our equation, right? Y. You can plug in a y value, right? Say we'll use 24 because we used that a second ago. So 24 then equals the slope, 2 over 25, 25 fifths, 20 fifths. There we go. Times x. What is the x that corresponds to that y? That's 24, and it corresponds to 20, right? Plus b. And now we have a variable to solve for. Okay. How do we solve for that variable? Super easy, right? Because the b is by himself. We want to get b by itself, so all we have to do is say 24. Oops. Let's try that again. We'll subtract this entire part right here from both sides. So then what happens is we have 24 minus 20 into fifths, 20 fifths, no wait, 2 25ths, there we go, 2 25ths. Wow, that was difficult for me. Times 20 equals b, and then we can solve for b now, right? That's great. We can solve for b now. So if we do this arithmetic here, right? So I don't really know if you guys remember, but a little quick review here. We have this thing called the order of operations, right? And most people like to remember it by using this little saying, right? Which is, please excuse my dear Aunt Sally, which is parentheses, exponents, right? Multiplication, division, right? Addition, subtraction. That's the order of operations. And when you're solving for equations, you definitely need to do that. You need to use the order of operations. In this case, for example, the first thing you would need to do here is to, since parentheses and multiplication is first, right? You need to multiply right there 2 25ths times 21st, and then subtract it from 24. And the order doesn't always, you can do it out of order sometimes and get it right, but you can do it out of order sometimes and get it wrong. Whereas if you always follow the order of operations, you will always get it right, right? So doing that, let me switch over to I was trying to decide whether or not I should show you on the calculator. I might as well do it. Okay, so let's see here. Calculator. We'll clear that out, right? Another reason why I really like this calculator, okay, is because you can use it with fractions, and you can see fractions very clearly on the calculator. So to put in the fraction 2 25ths, right, into this calculator, what you do is you use the parentheses right there. You type in the 2 25ths as you see it, right, on the page. and that's a fraction, 2/25ths. And you want to multiply that by 20, right? You can actually also just put parentheses around it too, and it'll work as well. And then hit enter, and we get 1.6. You get 1.6, right? So now that we have 1.6, here's another really cool thing that this calculator can do, right? The next step actually is to subtract 1.6 from 24. So what you can do is type in 24, right? And it actually stores your last answer that you had in memory. So minus, and instead of adding in 1.6, typing it in, I'll just hit the second button and then hit the minus sign down here. It also has an A and S on it, so it stands for answer, and it says answer there, and that was my last answer. And I can hit OK, right, or enter, and it'll give me the answer. So that's super handy, that answer button, because let me just tell you, sometimes when you do calculations, the number's going to be really long, and you're not going to remember what it is, or you'll write it down wrong. But if it's saved in the calculator as the last answer you used, it's a lot easier to do the math, right? So there we go. What does that mean then? I'll go ahead and minimize this down so you can actually see the rest of the problem. There we go. B, or the y-intercept, equals 22.4. So that number right there, this value, this dot that we were just talking about right there, where the y-intercept is, the value there is 22.4. Well, that's really cool. That makes it very, very helpful for a lot of things, right? Let me show you why, especially when you have a graph. So let me clear this off. All right. If you recall now, our line of the equation, the line of this equation is now y equals the slope, which is 2/25ths, right? X plus the y-intercept, which is 22.4. But you're asking yourself, how is that helpful? There's two variables now. Actually, there's not two variables. It's there in the equation as two variables, but now you can figure out what any of the points on this line is, right? Any of them are, because you have the equation of the line. And you can figure out then what the corresponding y value is to the x value, because y depends on x, right? So for example, you have here, for example, let's say we want to do what was the number at 80, right? What is the volume of the balloon with the temperature right here is at 80 degrees Celsius. At 80 degrees Celsius, what is the temperature, right? Sorry, not the temperature. What is the volume of the balloon? Right? At 80 degrees Celsius temperature, what is the volume of the balloon, right? We don't know. Let's plug in and see. We want to know what the y is, because that's the volume. 2 equals 2/25ths, right? Times x, which, what is x here? It's 80, because that's what we want to figure out the corresponding temperature to is. Sorry, the corresponding volume is to that temperature, right? Plus 22.4, which is the y-intercept, right? Sorry, my 4s look like 6s, but that's okay. And now you just do this very simple math right here, and you can figure out what the corresponding volume is to the temperature of 80 degrees. All right, so let me go ahead and put the screen on the calculator on the screen again, and we'll clear it out here, and we'll type in the numbers, right? So y equals, which we don't have to put in the y equals part, but it's, remember the fraction, it's 2. Uh-oh, I lost connection to my calculator. There it goes. 2 divided by 25, right? 2 divided by 25, and then times 80. Remember earlier I said you don't have to put the times symbol in there. You can just put the parentheses, and it'll make it times 80, right? Plus 22.4. So here's another pro tip, right? To make sure that the order of operations is working on your calculator, which it always does, but just to make sure, I always like to put the parentheses in more parentheses. to make sure the calculator knows that, hey, you're supposed to do the multiplication first. Oops, that's a percent sign. There we go. Right? Make sure it does the multiplication first, right? So there I have parentheses open, 2/25ths, close parentheses to multiply, and then 80, close parentheses again, and then it does that part first, and then it adds the 22.4. And then we'll hit enter. So at 80 degrees Celsius, the volume of the balloon is 28.8 liters. Wow, that's a kind of a big balloon, I think. Kind of a big balloon. So, yeah. Pretty cool. Pretty cool. All right. So let's keep on moving. Why do we do all this stuff? What is the point of all this? We do all this so that we can measure things, right? So what are the kind of what are some of the things that we can measure? Well, we can measure things like volume, like we just did a second ago. We can also measure length, mass, temperature, and time, right? But in chemistry, we measure things usually using the metric system, sometimes with the SI or the standard international system, but mostly it's with the metric system, right? Mostly with the metric system. So you'll get very familiar with things like the liter, the meter, the gram, the degrees Celsius, and seconds, of course, right? But we'll also do a few things with the SI or standard international system too, which is Kelvin and kilogram, right? We actually probably do the most with Kelvin because the Kelvin is what we use for most of our constants and stuff. So let's keep going here. Not going to spend much time on this slide. So when we're talking about numbers and measuring things, we have to discuss two types here. Let me go ahead and go on to the next slide. Right. Oh, and I need to also minimize my my calculator so that you can see what's on the thing. There we go. Right. There we go. My face again is blocking part of it, but I'll write it on the side for you. Right. The first kind of number there is called the measured number, right? It's the thing that you're used to, which is that you most commonly hear, right? Are measured numbers. So like you're measuring something with a ruler right here, right? But when we have measured numbers, we have a certain amount of what we like to call uncertainty, which is a whole other class in itself, uncertainty, right? Because you never actually get the exact number when you're using a ruler, right? You never get the exact number. I'll give you an example why. Take a look at this ruler up here. You have this piece of wood here, right? You have that piece of wood, and you're measuring it, and it's between 4 and 5, right? Well, most people would probably say that it's 4.5, right? That looks like it's in between, so maybe 4.5 centimeters, right? But let's take a closer look down here. This now has tick marks in between the 4 and the 5 right here, right? So if you take a look right there, it's not even exactly at 4.5. It looks like it's actually on 4.55 right there because it's between the half line, the half mark right there, right? And the sixth mark right there, right? So that's what I'm talking about when you measure things. You're not even really sure because you always have a certain amount of uncertainty. And the reason why we're even talking about this is because in measuring chemistry that uncertainty is important, and we use that uncertainty to figure out how precise we are. And how do we do that? We have this thing called significant figures, right? Significant figures are important in chemistry. So let's talk about some significant figures. So these are some of the rules of significant figures. So the first rule is that any number that's not a zero is definitely significant, right? So if you look over here like 4.5 grams or 122.35 meters, right? those are all significant figures, right? So on the 4.5 grams, there are two significant figures there. On the 122.35, there are five significant figures there, because every number that's not a zero is definitely significant. The second rule is that any zeros between non-zero digits uh, are significant, right? Any zeros that are between non-zero digits are significant. So if you're looking at the 205 degrees Celsius, that's 3 significant figures. And then if you're looking at the 5.008 kilograms, that has four significant figures, right? And notice the reason why we even say this, one of the practical things about this is that it shows you that this scale that measured all the way to 5.008 grams can go that small. Like you can measure very small quantities using that scale. So the more decimal places you have, the more significant figures you have, and the more precise you can get with the amount of stuff that you put in there, like the amount of stuff that you weigh, right? Um, the accuracy, on the other hand, is a completely different thing because your scale could be completely off. But at least you know that this is very precise. It goes very small units on this particular scale or balance. Next, zeros at the end of a decimal number are always significant, right? So here we have 16 mils or 16.00 mils, right? And therefore, that's got four significant figures, right? 50 here, right? Behind that number there, two significant figures there. Again, having these zeros here behind the decimal point tells you how precise the instrument is, how small you can get with it, right? And then you have any number written in the coefficient, right? Any number is written in the coefficient of scientific notation. What is the coefficient of the scientific notation? That is this number right here. That is the coefficient. This part right here is the exponent, but this part right here is the coefficient, right? So this coefficient in the scientific notation is 4.8. It's got two significant figures. This one here is 5.70, right? That entire thing is significant right there. So that's three significant figures, right? Pretty interesting. Again, that tells you how precise an instrument is when you're using it to measure something, okay? So the next thing is, what are the zeros that are not significant, right? So any zeros that are at the beginning of a number are not significant, right? At the beginning of a number. You can't see what's going on over here, but the example number it has in there is 0.0004 seconds, right? I don't know a stopwatch that can count that precise as far as seconds go, but since no numbers that are at the beginning of a decimal number are significant, that means this guy only has one significant figure, right? And then the other example it has is down here for is any zeros that are used as placeholders in a larger number. None of those are significant, right? So if you have something, and notice that there's not a decimal point here. If you have something like 850,000, how many significant figures do you have there? Well, all non-zero numbers are significant, so the 850 part, God, I can't even see that. Let me write that again. 850,000, right? All non-zeros are significant, so there's two right there, but these are all placeholders, so those are not significant. So this also has two significant figures. Very important in doing chemical calculations. The next thing to talk about, we just talked about measured numbers, right? The next type of numbers that we want to talk about when we're doing this kind of stuff is called exact numbers, right? What are exact numbers? Exact numbers are things that are defined, right? That you can count, basically, right? So basically, like I said, if you have 8 donuts, you have 8 donuts because you counted. That's an exact number. Or 2 baseballs, or 5 capsules. Those are all exact numbers. But the more important thing that are exact numbers that you need to realize are things like metric conversions or any kind of unit conversions, because we know for a fact that 1 liter equals 1,000 milliliters, or 1 foot equals 12 inches, or 1 meter equals 100 centimeters, and so on, right? That's the important thing. Remember that they are not measured, right? They also do not have any effect on significant figures, right? So when you're doing a calculation and you have to use a metric conversion or a unit conversion in it. It doesn't matter how many significant figures are in the actual conversion because those are all exact numbers. You don't have to worry about it. They're not measured numbers, right? So those are those last 2 points right there. Just make sure you know that. So one of the things that's not on here that I forgot to put on here is the PowerPoint is constants. Constants are also known as exact numbers, right? And the constant that we already talked about before, a couple of the constants that we already talked about before, is Avogadro's number. Hey, look, I actually spelled it right this time on my notes. So Avogadro's number is 6.02 times 10 to the 23rd. 23 zeros, I still don't know what that's called, right? It doesn't have any units on it, but that is an exact number that we know. And then the other one that we talked about that was a constant that we already discussed is the ideal gas constant. The ideal gas constant. And the ideal gas constant is actually 0.0821. And it has units. I told you these units already before, but we'll review. ATM over, or ATM liters over moles Kelvin, right? So those are also known as exact numbers. These will be very useful to you when we do our calculations in class, in your in their assignments and your exams, right? These will always be available to you. You don't have to memorize these. I will do my best to make sure that they're popping up right when you take your test or your exam, right? These will always be available to you, right? Now we're going to talk about density. Really interesting stuff. Okay, so let's talk about density now. Density is defined as, let me get my thing going here. Density is defined as mass of a substance divided by its volume. Right? Pretty simple concept there. If you look at the picture of this on the right, though, you can see that water actually has a density of 1. So when you put other things into water, you see whether or not things float or things sink. Well, that's because things that float have less density than water. Like a cork has a density of 0.26 grams per mil. Or aluminum and lead sink because they have numbers that are much larger than water. 2.7 grams for aluminum and 11.3 grams for lead. So that's why they sink. But this is the interesting one here. This is ice. Ice floats in water. We all know that. That's because it has a density of 0.92 grams per mil. Well, ice is just made of water, so how is it possible that it has a different density than water, right? Well, it turns out, though, that during the freezing process, when there's like crystals being made, ice crystals being made, the water molecules actually spread out, right? This is why when you freeze things, they expand. How many times have you put a bottle of water into the freezer for too long because you were just trying to get it cold, and you left it in there too long, and it bursts the bottle open? That's because water expands when it freezes. And it's expanding because its molecules spread out as it's crystallizing. And that makes its density lower. And when that makes its density lower, hence it floats in water, right? So density is a cool thing. So in chemistry, we normally, like I was saying before, measure things, measure temperature using either Celsius or Kelvin scale, right? Units. Fahrenheit's very rarely used in chemistry. But it is still good to know how to convert between the two. So this is just a chart of some interesting conversions between all three. So the equation to convert Fahrenheit into Celsius is Fahrenheit equals 1.8 times Celsius plus 32. Okay. I actually learned it as 9/5 here, because 9/5 is actually the same thing as 1.8, but in fractions, right? It's the same thing. And the reason why I learned it that way is because when I was taught how to convert Fahrenheit into Celsius, right? When I was taught how to do that, or vice versa, I was taught it using a graph. So if I put Celsius on the x-axis and Fahrenheit on the y-axis, right? And let's say we use body temperature, so 37 degrees Celsius, 98.6 degrees Fahrenheit. 37 degrees goes there, right? And 98.6 degrees goes there, right? That's a point, right? Because those two are equivalent to each other. But then I can go up here to boiling point, which is 100 degrees Celsius. And up here is 212 degrees Fahrenheit, right there. And I can put another point, because those two are equivalent, right? And since those two are equivalent, I can actually draw a line in between. And it turns out that every single spot on this line is a Celsius to Fahrenheit conversion, right? Every point on that line. And it turns out that this 9/5 right here is actually the slope of this line. I don't know why I drew it that way. Forget that part down there at the bottom. Right? Is a slope. And in this slope, right, the 9 goes there, and the 5 goes there. Wait a second. That F equals 1.8 times C plus 32 sure does look like something crazy. It actually looks like what we learned earlier, which is the Y equals mx plus b equation of a line. Right? Equation of a line. That's this line, right? So check this out, right? That 32 right there is the y-intercept, which means if you extend this line out a little further, right? A little bit further, this line crosses the y-axis at what? 32 degrees Celsius, right? 32 degrees Celsius. So interesting. And what is this right here then? On the 32 degrees Fahrenheit, right? 32 degrees Fahrenheit. This spoke there, right? 32 degrees Fahrenheit. So what is it on the Celsius scale if you went down here? This then is 0, which is the freezing point, right? The freezing point of Celsius. And if you look over here, the freezing point of Fahrenheit is 32 degrees Celsius. And the freezing point, 32 degrees Fahrenheit. I keep on saying Celsius because that's all we use in chemistry. But 32 degrees Fahrenheit. And then we look over here, the freezing point of water in Celsius. I just said it again. 32 degrees Fahrenheit. And then we look over here, the freezing point of water in Celsius is 0 degrees Celsius, right? So you can actually use a graph to do a temperature conversion. Pretty cool. And then it's actually really easy to convert from Kelvin to Celsius, because Kelvin actually just equals the Celsius temperature plus 273. What happened there? 273. That still looks like 230. There it is, 273. Except you couldn't see it anyway. So let me write this over here. Kelvin equals the Celsius temperature plus 273. And that's how you get the Kelvin temperature. Measuring the temperature of things takes us to then talking about energy, right? So what is energy? Energy is defined as the ability to do work, right? And it can be classified into kinetic or potential energy, right? So, for example, running water is potential energy because you can use running water that goes into a dam, right? That goes through a dam, and that makes electricity, right? But the interesting thing about that is that there's potential energy in that too because a dam usually has the ports where the water comes out very high, right? And that dam isn't moving at all. But since it made it that way, that high, it made the water go up that high, and that's actually potential energy, right? Being energy that's being stored because of it even says that right there because of a position of an object, right? So that's potential energy. So we also care about potential energy because there's energy in the breaking of bonds, right, in chemistry. So that's why in this particular definition, they're talking about also not just because of the position of an object, like I was talking about the water at the very top of the dam, but it's also the chemical composition, right? So I'm sure you've heard of ATP, adenosine triphosphate, which is the energy molecule that we use in our bodies or in any living body, right? We'll talk a lot more about that later on in the semester. But you get your ATP, right, from uh, you get your energy from a phosphate breaking off of the ATP molecule, right? Adenosine triphosphate. So we'll talk about that more detail. There's energy in chemical bonds that get broken. So we can actually measure the amount of energy in something based on a unit called a calorie, right? The calorie, little c calorie, right? And that is a calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius, right? So it turns out that that number is this 1.4 4.184 joules, right? So that's 1 calorie. You can actually convert between 1 calorie and joules, which is another unit of energy, right? And it is 4.184 joules. Okay, 1 kilocalorie, right there, is actually the same thing as 1,000 calories, which is actually the same thing as one big C calories, right? Because one big C calorie is known as a nutritional calorie. Yeah, this is a nutritional calorie. It's a nutritional calorie, right? So when you're looking at the facts on the food facts thing, the nutrition facts thing on the side of boxes of your food that you're eating, those are actually all in nutritional calories, which is actually 1,000 normal calories, or the same thing as 1 kilocalorie, right? Let's talk about specific heat then. The definition of specific heat is the amount of energy or heat needed to raise the temperature of exactly 1 gram of a substance by exactly 1 degree Celsius. So that should sound actually very familiar to you because that's the exact same definition that we gave for the calorie, right? The difference is that instead of just any substance, it's actually water, H2O, right? And the number we gave there for the calorie in joules was 4.184 joules. So it turns out that 4.184 joules is the specific heat of water. So it's pretty much all the same thing, or it is the same thing, right? But we can actually calculate calculate the specific heat for any substance, right? Using this equation that we have right here to the right. So let's do a little bit of an example here, right? We have 24.8 grams of some metal that we don't know what it is, and it's absorbing 275 joules of energy. The temperature change that occurs, right, when it absorbs that energy is 20.2 degrees Celsius to 24.5 degrees Celsius. So we just need to use this equation to figure out what the specific heat of this unknown metal is. We have the heat, which is right there. This is the heat. We have the mass of the stuff, whatever it is, right here. And we also have this, delta T, which is the change in temperature. That's the 24.5 degrees Celsius that came from the 20.2 degrees Celsius. right? That change in temperature. So let's go ahead and plug in the equation. Specific heat then equals 20, or 270 rather, 5 joules over 24 grams, 24.8 grams, times the change in temperature, which is 24.5 degrees Celsius, minus 20.2 degrees Celsius. Some quick and easy arithmetic here tells me that this part in the parentheses, 24.5 minus 20.2 equals 4.3 degrees Celsius. That's the delta T, or the change in temperature. We'll put the rest of it into the calculator to figure the rest of that out. Let me switch over to the calculator view so you can see what I'm doing. There we go. Right? So it's really important here that you use your parentheses, because we definitely want the calculator to know to do this arithmetic, this subtraction of the delta T, or change in temperature, first before it does the multiplication in the denominator, and then before it does the division with the numerator, right? So this is how we would type it in. 275, right, divided by, this is where we start opening the parentheses up here, 24.8, and we want that to be multiplied by, we'll want to open this parentheses again because we want to have the stuff in here to happen first. Open parentheses 24.5 minus 20.2, and that should be it, right? So if you look at the calculator the way I typed it in, if we're using our order of operations, we know that the parentheses are going to tell the calculator to do the arithmetic in here first, the 24.5 minus the 20.2 first, and then it will multiply the 24.8 grams, then it will divide with the 275. And our answer that we get from the calculator is 2.578 ... some numbers, right? Well, we have to use our sig figs here. There are 3 sig figs here with the heat. The mass has 3 sig figs as well, but the change in temperature only has 2 sig figs, right? So we're going to have to change this to be 2 significant figures. How do we do that? That will be 2.6, right? And the reason why is because if we look at the 7 here, the 7 actually rounds the 5 up to 6, and that's why we have 2.6, right? That's why we have 2.6. Good, good. And then also don't forget the units, because sometimes I even forget the units here. I was just thinking about that. This unit's going to be joules per gram Celsius, which makes sense because that's 2.6 joules for every gram for every degree Celsius, right? That's why it's the unit. Very interesting stuff. There we go. We can talk about the heat of fusion, right? The heat of fusion. Well, what is actually the heat of fusion then? The heat of fusion is actually the energy required, or that must be added to convert exactly 1 gram of a solid to a liquid at its melting point, right? So we'll use water as our example here. Excuse me. We'll use water as our example here, and for water, 80 calories or 334 joules of heat is required, right, to melt 1 gram of ice at 0 degrees Celsius. That's its melting point, right? So that's why we have here in our heat of fusion equation, if you have solid ice plus 80 calories or 334 joules per gram, the solid water or ice becomes water. And this is actually a reversible reaction, right? Because you can do it the other way, where if you had liquid water and you froze it into solid water, you get out of it the same amount, 80, 80 calories per gram of water and 334 or 334 joules per gram, right? So let's try to figure this out. What if we had 32 grams of ice, right? What if we had 32 grams of ice? How much energy is required to melt that guy, right? Well, that's super simple. So again, uh, we'll use the some dimensional analysis and some unit conversions. We'll start out with our 32 grams of water, H2O solid, right? That's what that is, H2O solid. And that's times the amount of energy that we're putting into it to melt it. So again, we always use, chemistry likes to use joules, so we'll use joules. That's 334. I wish I looked more like a 3. There we go, 334 joules for 1 gram, right? The 1 gram comes from this gram right here. That times the conversion, right? Because we always want our answer to be in kilojoules. For every 1 kilojoule, there's 1,000 joules. Because remember, for some reason the SI unit is like joules, right? Or kilojoules. So we'll go ahead and do that calculation there. I'll switch back over to the calculator view. And I'll start out by clearing our last calculation. And we have 32 times 334 times 1, right? And I could have put parentheses there, but I'll just go ahead and go enter, and then we'll divide that number by 1,000. And that gives us 10.688, right? So we needed to be 3 sig figs, right? Because our smallest number of significant figures is there, 3 significant figures right there, right? Which means that is going to be then rounded up to 10.7 kilojoules. That's how much energy is required to melt 32 grams of ice. Fun stuff. This is the last slide. So if you're looking at water, right, the thing just to know about heating and cooling curves is that when water is boiling, until all the water is boiled, that the temperature of the water is always going to be at 100 degrees Celsius, right? So there'll be water that's in gas phase and water that's in liquid phase, both at 100 degrees Celsius. The same is true at the melting point too. There'll be water that is frozen at 0 degrees Celsius and water that is still melted at 0 degrees Celsius, right? So it's important to know that when they're going through their phase change, these different substances, in particular here with this water, right, when they're going through their phase changes, they actually stay at their phase change temperature, whether it's the boiling point or the melting point, until all of it has happened. All of it has converted over, right? The same is true still when you're going the opposite direction. When the steam, not opposite direction, but when instead of melting and freezing, or it is the opposite direction. So this is solid ice melting and then boiling, right? It's still true if you go in the opposite direction, where the steam actually condenses. When the steam condenses, right, at 100 degrees Celsius, you still have water molecules that are completely in the vapor phase up there with the steam, but some of it is liquid phase under the condensing line, but it will, until all of it has condensed, it's still at the 100 degrees Celsius. And then if you travel even further, get it colder, and you freeze the ice at 0 degrees Celsius, you will have molecules of water that are still liquid here, but then down here you'll have molecules of water that are frozen. But until it all freezes, they're all still at 0 degrees Celsius. That's why you can't keep a freezer at 0 degrees Celsius. Most freezers are like minus 20 degrees Celsius. Otherwise, you'd have everything melting in your freezer. That being said, that actually, I believe, ends this lecture. Thank you for sticking with me for all this time. Your homework assignment is posted on Blackboard, and good luck. Thank you.